Hello, today I'll be showing you guys how to do problem 2.26 from Grittith's Introduction to Electrodynamics. Now problem 2.26 reads a conical surface or an empty ice cream cone carries a uniform surface charge sigma. The height of the cone is h, and as is the radius at the top. Find the potential difference between the points A, the vertex, and B, the center of the top. Alright, so I already drew out our cone here. So we have a cone with the vertex is A, and the center of the top is B with a height of h, radius of h. And then our goal is to find the difference between the potential of A and B. Alright, so now, first off, we'll start with finding the electric potential at A, which is the easy one. And we know the equation for the electric potential as 1 over 4 pi epsilon naught times the surface integral of the surface charge over our separation vector A times dA. Okay, so one of the first things I'm going to do is to cut our cone into a sort of triangle shape. It's to define it into 2D. Make solving parts of this problem a bit easier. So we have a triangle, height h, and this top part is h, and this is our A. Okay, so to do this problem, we're going to be working in spherical coordinates with our origin centered at the vertex at A. And then from this triangle, we can already figure out some parts. We can find this angle here, and we can find the length of this the hypotenuse of this triangle using Pythagorean's theorem. This is going to give us h root 2, and to find this theta, we're just going to use tangent, which is going to be h over h, which is 1, so that means our angle here is going to be equal to pi over 4. Okay, and then since we're working in spherical with the origin at A, our separation vector of A is just going to be r, so I'll write that as mu r. And so now our next step is going to be trying to find our differential area element. Now we know our theta is constant at pi over 4, so that only leaves us with our phi and our r terms. So dA is going to equal to phi dLr, and phi is going to be comes attached with an r sine theta, and then dr doesn't come with anything. So we know our theta is equal to pi over 4. So our dA becomes r root 2 over 2 d phi dr. Okay, so now we can plug all this in to our equation of VA. And then take out the charge because it's constant. 4 pi epsilon naught. And our phi ranges from 0 to 2 pi. And our r ranges from 0 to h over root 2. Okay. And then so we have 1 over script r of A, which is going to be 1 over r, times our dA, which is r root 2 over 2 d phi dr. Okay, so now these r's cancel out. We can bring this root 2 over 2 out. So we'll have, root 2 over 2. Now we have no phi terms, so we're going to be left with 2 pi when we get back the integral, and we have no r terms because they canceled out, and so that's going to become h over root 2, or h root 2, sorry. Okay, so this 2 pi we cancel out with this 4 pi and become 2, and this 2 we multiply, or this root 2 multiplied this root 2 is going to become 2, which will cancel out this 2 at the bottom. So we'll be left with our VA is equal to h times our surface charge over 2 epsilon naught. Okay. So now our next step is to find the potential at B, which is going to be a little bit harder, but we'll start off with the same way as doing VB is equal to 1 over 4 pi epsilon naught times the surface integral of our charge over separation vector of B times dA. Okay, so I'll start off with another triangle. Drew it a little bit bigger because you need to see this a bit more. So this time we have our B up here. This is still H. This is theta and H root 2. So what we'll be doing is the surface charge is, we're sort of splitting up this cone into a bunch of like really thin circles. And then so our separation will be, a separation vector for B will be from here to the circles that we are splitting this cone up into. So on this triangle, the circle is going to be drawn sort of around like this. And so our separation vector B will be along here. Okay, and then we're still working spherical with our origin down here. So our R is going to be the length of this side here. So now we made a triangle with a leg of H, of R, and script RB with an angle theta here. And then we can use the law of cosines, which I'll come back to over here. Actually, I'll just work on a new piece of paper, just so it's not too messy. Alright, so now, law of cosines using our triangle down here, that is going to give us script RB squared, which is equal to R squared plus H squared minus 2RH cosine theta. Okay, now we know our theta is equal to pi over 4. So we can plug that pi over 4 into this cosine, which I'm going to write this as 1 over root 2. And then I'm going to take the square root of both sides. So script RB is equal to the square root of R squared plus H squared minus 2RH over root 2. Okay. So this is our new script RB term, which we can use for this equation over here. But our differential area is going to be the same as part A, because nothing really changes for our differential area. But that means we need to take our integral in terms of R, which is just going to be quite hard, having R in the bottom here when you plug in script RB. So to make the evaluating this integral a bit easier, we're going to be using a couple of trig substitutions. So what we will start with is repeating the square with this one and this one, which will give us the square root of R minus H over root 2 squared minus H squared over 2 plus H squared. Okay. And these will give us H squared over 2, so that means our script RB is going to be R minus H over root 2 squared plus H squared over 2. Okay, so now this is where our trig sub is going to come in. We're going to make a triangle with these as the two sides. So we'll have a triangle over here with a angle of alpha, with one side as going to be the square root of this, so h over root 2, and the other side the square root of this, which is r minus h over root 2. Alright, so then we can write tangent of alpha equal to r minus h over root 2 over h over root 2. And we write that as h root 2 tan alpha is equal to r minus h over root 2. So now we can plug h over root 2 tan alpha into r minus h over root 2 over here. So now this will become the square root of this squared, so I'm just going to write h squared over 2 tangent squared alpha, and then I'll bring down the h squared over 2 here. Now we can take out h squared over 2 of the radical of the square root, sorry. So that'll become h root 2 times the square root of tangent squared alpha plus 1. You know, using trig identities, that tangent squared alpha plus 1 is going to be secant squared. So h over root 2 times square root of secant squared alpha, which will give us h over root 2 times secant alpha, which is our script RB term. Okay, so now that is our new script RB term, but we would also need to substitute in our differential area. We need to find what dA would be in terms of our trig sum. So we'll come back to over here, and we'll move h over root 2 onto both sides, or onto the left side. Tan alpha plus h over root 2 is equal to r. Right, and then so we'll have h root 2 times tan alpha plus 1 is equal to r. Now we can, wherever we see r, we can plug this equation in, and then we can also need to take the derivative in terms of alpha to find our to replace dr with. So we need to alpha of h over root 2 tan alpha plus 1 r alpha. So this is going to become h root 2. The derivative of tan alpha is going to be secant squared alpha equal to dr d alpha. So dr root 2 alpha. Okay, so that's what we're going to replace our dr with when we write our differential area element. So let's move on to the next step, which is finding our upper and lower limits of our integral, since we're replacing dr with d alpha, which we will use this equation to figure out. So our alpha upper limit is gonna be when r is equal to h root 2. So that will give us h root 2 times tan alpha plus 1 is equal to h root 2. Right, so we're just plugging in h root 2 into r over here. Now this will give us tan alpha plus 1 is equal to 2. Tan alpha is equal to 1. So that means alpha is going to give us pi over 4, our upper limit for alpha. Now for our lower limit of alpha, use the same equation, so h over root 2 times tan alpha plus 1 equal to 0. Now this h over root 2 is going to be eaten up by the 0, So tan alpha plus 1 is equal to 0. We have tan alpha is equal to -1. That leads alpha, our lower limit of alpha is going to be equal to -pi/4. So now we have everything we need to plug into our integral of. Now, before we do that, I am gonna rewrite I'm gonna write out our differential area element again. So dA is gonna be equal to d phi dr. So phi is gonna be attached with r sine theta d phi dr. But we know dr is now gonna be this term over here. So, and then we know sine theta is going to be √2/2, and then dr, so h over √2 times secant squared alpha, d alpha, d phi. And that √2 is going to cancel out that √2, and then we have an r here, which we can plug in this equation over here for r, which will give us h √2 times tan alpha plus 1. And then we'll have h over 2 secant squared alpha d phi. Okay. Then we can look again, plug in this differential area into our integral over here. So BB is equal to, let me take out the surface charge, 4 pi epsilon naught times the surface integral. Phi remains the same, 0 to 2 pi. This time we have alpha is equal to -pi/4 to pi/4 times 1 over our script RB, which is h over 2 secant alpha. So 1 over h √2 secant alpha times our dA, which is going to be h over √2, or well, h squared to √2 times tan alpha plus 1 times secant squared alpha d phi d alpha. Okay, so we can start canceling out some things. This h squared is going to cancel out that h. This √2 is going to go up to the top and cancel out the √2 down there. Okay, one of these secants will cancel out the squared here. Okay, and then so now we can start pulling out the constants and also evaluate the phi integral since we have no terms of phi. So we'll have, bring this down. The phi is going to turn into, or the phi integral is going to turn into 2 pi. And then we'll have a h over 2 term, and then we'll write out the integral, pi/4, -pi/4 of tangent alpha plus 1 times secant alpha d alpha. Okay, so now this 2 cancels with that 2, that pi cancels with that pi, and then we are left with this integral, which I will distribute the secant out. So we have h sigma over 4 epsilon naught. Then we have integral pi/4, -pi/4 times secant alpha tan alpha plus secant alpha d alpha. Okay, we're almost done. So now we take the integral of these two. Now the integral of secant alpha tan alpha is just going to become secant alpha. So we'll first off bring this down. So this is going to become secant alpha, and the integral of secant alpha is going to become the natural log of tan alpha plus secant alpha. Okay, now we evaluate this from pi over 4 to negative pi over 4. Okay, so now we'll start plugging these in. So h, so not secant of pi over 4 is going to give you square root 2. Ln of tangent of pi over 4 is going to give you 1. And then secant pi over 4, which is root 2. Now move on to the second thing we plug in. So secant of negative pi over 4 is still going to be root 2 plus the ln of tangent of negative pi over 4 is going to give you negative 1, and then plus root 2 again. Okay. Now I'm going to distribute this negative out. Here comes that. And then we'll add these two terms together. So that root 2 is going to cancel out that root 2. So I have h epsilon naught times the natural log of 1 plus root 2, or sorry, minus the natural log of root 2 minus 1. Okay, so now the next thing I'm going to do is multiply the insides of our natural log terms by root 2 over 2, which will give us natural log of root 2 plus 2 over root 2 minus the natural log of 2 minus root 2 over root 2. Now, properties of logs, we can put this over each other. So h for epsilon naught times the ln of root 2 plus 2 over root 2 divided by the inside of this, which is 2 minus root 2 over root 2, which will give us h times surface charge times 4, or over 4 epsilon naught, times the natural log of root 2 plus 2 over 2 minus root 2. Okay. Alright, so the next step from here is multiplying the top and bottom by root 2 plus 2 to simplify the whatever's in the natural log. So we're going to have h sigma over 4 epsilon naught times the ln of root 2 plus 2 over 2 minus root 2, so times root 2 plus 2. Alright, so this is going to give us h sigma 4 epsilon naught times the ln of root 2 plus 2 squared over 2. Okay, so I'm going to bring everything under the squared here. It's going to be h sigma 4 epsilon naught times ln of root 2 plus 2 over square root 2. Alright, so then property of the logs, I can bring this 2 out, which will go as h sigma 4 epsilon naught 2 ln of square root 2 plus 2 over square root 2, and then multiply this top and bottom by square root 2. So this 2 on the outside will cancel with a 4, and we'll get ln of 2 plus 2 root 2 over 2. Those 2's will cancel out with each other. So then we'll have our final equation for electric potential at point B as h times sigma 2 epsilon naught times ln of 1 plus square root 2. So now we can go back to the very beginning of finding the potential difference between A and B, as VA minus VB, which is H times the surface charge times over 2 epsilon naught minus what we just found, ln 1 plus root 2, which is H 1 minus ln, which is the potential difference between point A and B, which is H, height of the cylinder times the surface charge over 2 times epsilon naught times 1 minus natural log of 1 plus root 2.